let's start recording. Yes.
Are we covering new material? You're saying we still have material to cover, is that?
Yes, we're covering. Yeah, absolutely. We're covering new material today. We're covering the last topic, which is a certain example of a problem with race conditions, with a racetrack problem, right? So, and we're also covering this another version of flip-flop gate called a JK gate. But I will cover them quickly, and then we'll have time for review. And the way I'll do it, I'll basically just go through the topics that definitely are going to be on the exam, so you'll know what they are. And I'll post those slides as well. Can you still hear me?
Yeah, we can hear you.
Okay. Okay, but the screen disconnected. Okay, hold on. I may drop out for a second. Okay. Can you hear me and see my screen now?
Yeah.
Yeah.
Okay, great. Wonderful. Okay, so let's start with the flip-flop gate, then I'll go to the racetrack problem so that we'll do it sort of step by step. We don't need that. We do need that. Oh no. Okay, so the disconnection disconnected me from iCloud, but it's okay. I'll restore it very quickly. Don't copy my password. You can see it. Oh my God. Okay. I apologize. Text me. No. Bad connection. Any questions while I'm doing this that I can sort of answer this?
Professor, will you have office hours today?
Yes. We'll have to be efficient about it because I have my other lecture after this. But yes, now I will try to have office hours right after the lecture. But if we don't fit into it, we can have additional office hours after my second lecture. But everybody who will need additional office hours needs to let me know or send me an email. But I'll try to talk to as many of you as possible right afterwards. Okay, so we go to Keynote.
Professor, was there homework due today?
There was no homework due today. I didn't want to, so I want you to start reviewing. But so I'm going to, so during normal semester, I do assign homework and then go over it. But right now, I will use it as just a lecture. I will use as so you didn't have to.
What homework? Sorry, do you know what homework 18 is? That's due today.
Let's use it as a reserve for, so there were a couple of people who missed some of the other homeworks. So use that link to submit anything that you missed. But I did not assign homework for today. Okay, so here we are.
I think the homework 18 was for yesterday, and it was just doing the truth table for the flip-flop gate with the NAND instead of the
with NAND. Yeah, that's right. That's right. Thank you, Patrick. Too much going on. Okay. So that was like a very short homework. Okay, so we're going to do flip-flops, racing problems. So we'll need this one, and we'll need one more. We'll need review on this one. Okay, almost ready to start. I'll try to give plenty of time on the exam, but if you run out of time, one thing that, oh, actually, this is what I wanted to propose. So, the exam is supposed to take the regular class time, which is 1 hour and 34 minutes, and supposed to start at 11:40 regular class time. What I propose I do, why don't we start at 11, so that you have an extra, 40 minutes, right away. So if I tell you that we start the exam on Monday, like earlier at 11, is there anybody who cannot start at 11? Please let me know now. Or who? So everybody can start at 11.
Class at 11.
Okay, and your class ends at 11:40.
It ends at 11:30.
Okay, so I obviously would not end it early. Like I would still go until 1:15, or I can even go until 2. I just want, there were students who like knew what to do, but they were pressured by time, and I don't want that to be an issue. So let's set that aside. Let's get back to that. But other than who is the student who has a class until 11:30?
Alan.
Alan. Alan, would you mind? Would you mind if we started at
No
11
problem.
and
It's fine.
and then you join at 11:30? No rush, right? And then you can have as much time as you need, right?
Yeah.
Okay. Okay.
No problem.
Yes.
Okay,
Okay.
it's
Very
fine.
good. Very good. So yes, I welcome people to join at 11. If you join later, that's fine. I don't want anybody to feel time pressure. Okay. I want everybody to do as well. So this is the last thing. Yeah, I didn't assign this as homework. I just want to explain it. So this is what we call a JK flip-flop gate. As you will see, it looks very much like a T gate, right? Where we only have the clock input, right? Except that we now have J and K that are ANDed with the Q and Q prime feedback that would be the only thing going into S and R in a T gate, right? So now these S and R inputs, in addition to just feeding back from Q and Q prime, we also have J and K. Okay, so this is the same thing, just blown up a little bit. And let's consider the truth table for this, right? How would it, play out? So first, let's consider that case that really shouldn't happen when both J and K, or if they are S and R, set and reset, they're both ones, right? In the previous flip-flop gates, we either just decided that this condition is never going to happen, and then we had another flip-flop gate that sort of prevented that condition from happening. And here we say, okay, it's possible. So let's see what will happen to this JK flip-flop gate if both J and K are 1. Well, if both of them are 1, then it effectively, well, let me ask you. So we have 2 1s going into these 2 ends, right? So J is 1 and K is 1. Right? What happens? Why can I assert that if both J and K are 1, then this JK gate becomes a T gate, right? Where we only care about the clock input. Who can explain this? Just quickly. Right? What makes that so are these 2 ends. So 1 is identity for AND, right? So if one of the inputs for AND is 1, that means that the outcome of AND is going to be its second input, right? So if both j and k is 1, then what is going into S and R are q and q prime, right? And this is what it looks like. And in the previous lecture, we called it a T gate, right? And it's the gate that simply alternates with the clock, right? Except at twice as slow. So this is a T, flip-flop in which output Q oscillates 2 times as slow as the clock itself, right? If you remember the the oscillation graph. I don't want to exit this lecture because then we'll have to wait until the other loads. But who doesn't remember, right? So we have the oh, okay. I have to let the plumbers in again. Just hold on 1 second. Okay, I'm back. Apologies. There should be no more interruptions. Any questions about what happened? What happens when we have a T flip-flop with the only input is clock, right? And S and R being fed back from Q and Q prime. Okay, so you remember, we just covered it yesterday. Okay, so that is what happens when both are 1. But what happens if it's a more normal condition when they're both either 0 or if only one of them is 1? Right? So here we have the truth table for the remaining possibilities, right? So when j and k are 0, then the previous state, right, as with any flip-flop gate. Question? Somebody's mic? Okay. All right, so that's pretty straightforward. Now, what happens if only k is 1 and j is 0? If j is 0, right, then S becomes 0. And that's where, and it's going to be fixed at that, right? So with any flip-flop gate, right, as soon as you send a signal, it sets to something, and then it's fixed at that until a new signal is set, right? So if j is 0, right, S will be fixed at 0, right, and Q will become 0, right, because that's what any flip-flop gate does, right? So, but 0 was the original value of j, right? So we can write down both that when j is 0, which means that k is 1, right? Basically, k goes into R, which is the reset that is supposed to reset q to 0. That's exactly what happens, right? There's nothing new about that, right? So when j is 0 and k is 1, then the gate is 0, q is 0, which is also the value of j. Okay. In the opposite case, if k is 0, there is no signal to reset, but j is 1, there is the signal to set. Then the gate, or q, becomes 1, right? Which is also identical to j, right? So we can express this truth table as, in these 3 possibilities as previous state, and then these 2 both are value of j, right? If you want to express it as 0 and 1, it's going to be 2 rows. But if you can be agnostic about it, you could just say that the value of j is preserved.
Wait, sorry, I'm a little confused on this. If j is 1 and k is 0, when k is 0, right? Since it's AND, that means R should be 0, which is and then Q naught would be 0. Since S is dependent on J and Q naught, wouldn't...
Just 1 second. Let's go slow. So we're talking about the last row, yes?
Yeah.
Okay, so in the last row, J is 1, K is 0. Okay.
Yeah, so since K is 0, R would be 0 because it's 0 and end no matter what. It's gonna be
Absolutely. If K is 0, R is 0, correct?
0. And then Q naught is 0 in that sense, right?
No.
No.
If R is 0, then Q is 0. I'm sorry. Yeah. No, you're right. So
Yep.
if R is 0, then Q is 1 and Q prime is 0, correct?
Yeah, so Q prime is 0, and now S is dependent on J and Q prime. Now J is 1, but if Q prime is 0, 1 and 0, isn't that 0?
But keep in mind that the gate itself is stable, right? So this inner rectangle is stable. The outside part, actually, it's a good point. Yeah, that's actually an excellent question. The outside part only switches with the clock, right? Because the clock is the input. So basically, it will wait until the next cycle, right? So this feedback doesn't happen until next cycle, right? So the only so before, when we were looking inside each flip-flop gate, right, inside this rectangle, right, it had to stabilize, right? So after we do a single pass, we can just keep going, and it's going to remain stable. But that is not the case with whatever happens outside of a flip-flop gate. And that actually nicely brings it into the racetrack problem that we're going to talk about next, right? So this whole thing is not the flip-flop gate. The flip-flop gate is just inside the box, right? Where we're sort of working with it in time with the clock input. Now, but when we do put it together, so maybe if it's not entirely clear, just hold that thought for a minute, right? Then we can express the answer like this. What do we have? We have that if both J and K are 0, previous state is preserved. If K is 1, then the whole thing gets the value of J, which is 0. If J is 1, K is 0, the whole thing will also have the value of J, which is 1. Okay? And then the last possibility, when both J and K are 1, this JK flip-flop turns into effectively a T flip-flop, where the outcome Q simply oscillates with the clock, except that at half speed. And that's all about the JK flip-flop, right? So you know what? Let's open the T flip-flop so that we can see it also. It is a review core class anyway, so. Right, this is the oscillation that I'm talking about. Where we have Q and Q prime feeding back directly into S and R, and the only external input is clock, right? So the change only happens during this red line, the attack, the surge of electricity, right? And that is when the clock is 1, right? And for the rest of the cycle, clock is 0. It results with Q, right, oscillating with the clock, but twice as slow. So the clock goes 1 0 1 0 1 0, and this goes slowly 0 1 0 1 0. Okay. All right. So we can come back to the JK flip-flop, but now let's do the last topic that we do have to cover, and we will consider the racetrack problem. We consider it in context of shifting bits in a register. So to do that, we have a device where we have multiple flip-flop gates, and they're all connected to the same clock. Okay, this is taking a little longer than I hoped. Okay, while it's loading, let me just explain the concept, right? So what happens is that when you have multiple flip-flop gates, you want that are chained effectively, right? You want the signal from them to go sequentially, right? But they're all connected to the same clock, right? And the problem may occur if the signal of the computation will pass a single gate and go to the next one before this moment of surge in the clock finishes, right? And you may think, well, that moment of surge I told you takes like 1/1,000,000th of a second, right? It's very short, right? But it's actually quite likely that a flip-flop gate can sort of like change its state quicker than that. And that is the case because the electrical impulses in a circuit, they travel very fast. They travel like electricity in the wires. Does anybody know how fast electricity travels in the wire? Let's say like you plug in your toaster, from the wall to the toaster. How long does it take?
Is that a speed of light question?
Yeah, it travels pretty much at the speed of light, right? It may not be exactly, but pretty much at the speed of light, so very fast, right? And because your circuits are miniaturized, they're so small, and there's very little distance to travel, right? So it's this racetrack problem seems ridiculous, but it's an actual problem. And we're going to solve it in about 10 minutes. Very clever, easy solution. But right now, we are just aware of it, and we just assume that it's solved, and we don't have to worry about it at the moment. Okay, so here we have 3 flip-flop gates chained together, right? What does it mean, chained together? Well, it means that the state of the first gate becomes the signal going into the second gate. The state of the second gate, or the previous state, goes into the signal, or I'm sorry, set input of the next gate. Right? Now we call the first gate x1, the second gate x2, the third gate x3, right? So the x's refer to the whole thing, to the whole flip-flop. And then you notice that, so where I put x here, this is x1, this is the x2, this is x3. Now, but what it means, if you look here, when it's stable, whatever each of them, right?
So
That's
your mic
here, and
cutting
that
off.
is also, that is. Okay, so we're breaking up. You still see the picture though?
Yeah.
Okay. How's my voice now?
It sounds a little
Is my
delayed.
voice better?
Okay. Yeah, I think so, maybe. If you keep talking, I'll know.
All right, I'll keep talking. I'll try to go slowly. So I just want everybody to be clear at what we're looking at, because there is many lines and stuff. But basically what we have, just 3 flip-flop gates that actually, right, so they're just clocked flip-flop gates, right? You have the Q and the Q prime, those are the outputs. And the actual Q is what is considered the output of the value, the present value of the of the flip-flop gate. And for the first one, we can also consider it x2, x1, right? And it also, that resulting stable state of the first gate will go into S input of the following gate, and its complement will go into the R, right? So it's continuously ensured that are going to we'll be able to see the output here because it's split at every point, right? So as we will trace this, we will see at every point what the value of everything is. Now, the second and the third gate get their inputs from the previous gates. The very first gate will get its input from the in signal, right? So whatever it is, it'll go directly into the set input, and then its inverse will go, its complement will go into the R. So any question? Oh yeah, and of course and that is sequential. However, the clock signal goes directly in all three gates at the same time, right? So here, clock, right? So you have a bunch of devices, but they're all taken to the system clock, right? And that system clock, it goes with the one is very fast, and fast and furious, and then the rest of the cycle is 0. Okay, any questions, or you stop hearing me, interrupt me. We're going to initialize. Yep.
I see there's 2 x3s there. What is that?
Yes. Right. Good. I said that, but good question, because I'm going to repeat it. So the top axis, x1, x2, x3, they simply label that. I call this first flip-flop x1, and this is its actual input. It's really redundant. So you can pretend that the top axes are not there. They're just labeling the whole gate, right? Does that make sense?
Is
Yeah.
the x1, the lower x1, is that, did you say that's input or is that output?
Output, right? So what we see, the actual it labels below x1, x2, and x3, they're outputs. So x1 is the output of the x1 gate, right? It comes from Q, right? Q is the. I really didn't need to put the ones on top. They're confusing. But other than that, it's clear, right? Okay. So we decide that the initial state of these three gates, or we're just going to set them or reset them initially all to 0, right? Before we do anything, the Q, this Q, and this Q, and this Q are 0, and that means that x1, x2, x3 are 0. Okay. So now we're going to push a sequence of signals into the in, right? So we have a string of bits. It could be anything. In this case, in this example, it's 0, 1, 0, 0, 0. I have a string of 5 bits, right? And I'm going to send them one after another into this input, right? And it'll go, each one of them will first go into here, into the first gate, and its complement will go in the R of the first gate, then something will happen, it'll keep going forward, more, it'll keep going forward. So effectively, all of these values, one after another, will shift through all three of these flip-flop gates, and then eventually they'll go somewhere, whatever is next on the right. Okay, so this is what we're going to do. And at every strike of the clock, we will be able to see, like, imagine that we have like an electrical displays connected to x1, x2, x3. So at every clock tick, we'll be able to see what the values of these three flip-flop gates are. So we will be able to watch, in real time as it goes through, as it were. Okay. So this will allow us to see the shifting of the one as it progresses through these three flip-flop gates, right? Again, this input string could be anything, but I have a bunch of zeros and only a single one, right? So what we should see we should see that one going from one to another, and then there will be zeros on either side of it, right? So they start as 3 zeros, then I send another 0, then I set the 1, and then I send 3 more zeros, right? So we should clearly see this one traveling, shifting, right? And we are assuming that these gates are not, each one of them is not faster than the uptick of the clock, right? So, and in a minute, I'll show you how it's done so that it doesn't happen. Okay, and just to reiterate it, that when I say how it's done internally, right? So it's done inside the gate. So right now we don't need to worry about what's inside because we know how it works. Okay. Right. So again, so to lay out graphically, right, this racetrack problem is that, as I said, if, or I will show you why it could be a problem, right? So if we couldn't guarantee that the gate is slowed down, right? In fact, if there is no effort is made to slow it down, it will pass through the gate faster than the surge of electricity here, right? So if that happens, then instead of shifting, the signal being either 1 or 0 will traverse the flip-flops too quickly, right? Producing all outputs of 1 or 0, whatever it is, at the same time, right? So what would happen is that, let's say we have the 1, right? The 1 enters here, and then if it travels too quickly, it'll just shoot through all of them, and then it'll set all of them to 1, effectively erasing whatever bits were there before, right? And then the next bit will go, let's say the next is 0, and it'll shoot through them also, right, with the speed of light. Not just through one of them, through all of them. And just zero it all out, right? So what would effectively happen is no matter how many flip-flop gates you have chained, let's say it's a single byte, let's say it's 8, or let's say it's a kilobyte, right? It'll just shoot through all of them, or like a lot of them, and just set all of them to that one value, either 1 or 0. And that's bad, because any questions about that? This is why it's a problem or potential problem, right? So we're going to solve this later, but now we'll pretend that it's solved. Okay, so that our gates are guaranteed to be slower than the surge of electricity. So all of these SR control or clock, SR clock flip-flops are such that the time needed for the signal to go through a flip-flop gate is greater than the time needed for the clock to run the rising edge, from the low voltage position to the high voltage position. Okay, now next we will see how that works. Okay, but now let's trace the signal, right? So in the first phase, the signal goes inside flip-flop on phase 1 and out of it on phase 0, right? So what am I talking about? We can look at each clock cycle as having 2 phases. Phase 1 is the signal attack here. It's very quick. That is when clock is 1. And we'll call that phase 1. And the rest of the cycle, it's phase 2. The rest of the cycle, clock is 0. So the signal goes inside. So that means that the signal will enter each flip-flop gate during this phase 1. And then that's the fast phase. But then this long, like 1,000 times longer phase, right? That's when the signal will exit, right? So whatever happens to the input signal in the flip-flop gate, right, it will enter on phase 1, and it will exit on phase 0 that follows it. There will be no change in outputs during phase 1, right? So because we artificially slowed the gate down, right? Necessarily, whatever entered in the beginning of the phase 1, right, will not be able to exit until phase 1 is over, meaning until phase 0. Does that make sense right now? Yes. Okay. So no questions. Okay, good. So that means that the change of the output, meaning the Q and Q prime, that will not occur until we go into phase 0. So when we're going to trace time, then I'm going to have multiple cycles, right? So we have 5 bits. So we'll watch it in the system over 5 full cycles. Cycle goes from here to here, right? From phase 1 to the next phase 1. But then within each cycle, right, we have the phase 1 when the electricity is surging, and then phase 0 where clock is off, clock is 0, right? And what that means is that for each cycle during the first phase, the inputs change, right? The new inputs go in, but only in the second phase, phase 0, the outputs come out, right? And they're artificially sort of like separated or stacked sequentially, so there will be no jumping ahead, right? It's guaranteed that there will be no jumping ahead. Okay. So as I already said, the current state of all of these flip-flops is going to be set to 0. Oh, the previous state, whatever you want to call it. And we start the clock at 0, and our first input, this one, is 0, right? The next one is going to be 1, but the first one is 0. So we have clock is 0, the first input is 0, and then x1, x2, and x3 are 0, right? So we start with all zeros. Now, there will be no change in output during phase 1, right? For that reason, right? So this is our inputs; they're all 0, except for, of course, clock. For the first surge, right, it becomes 1. So clock is 1. The input is 0. The present states are 0, right? Now there will be no change in the outputs while clock is surging. That means that during that phase, the outputs will not change. Okay. Now, once the clock stops surging, now the clock became 0, right? So we went from clock being 1 to clock being 0. Okay. Now the outputs can happen, right? So we artificially slow down each gate to not have outputs until clock became 0, but now they can come out. Okay. So the S was 0 that came in, and it comes out Q is 0, X1 is 0, right? That's the output. What happens with X2 and X3 so far? Nothing, right? They stay as they are. Right? So I'll pause here. Right? So far, a single full cycle passed. Right? Clock surged. The 0 input went into the first gate. Right? Nothing has come out yet, so nothing went into the second and the third gate. Right? And that stayed the same. So my inputs, basically the bits that I have coming from the string, I have them in red. The green ones are what was there before we started the work. Now, when the clock went into the phase 0, right, that's when the input could into the first gate could come out x1. Now we go to the next cycle. So the clock goes to 1 again. And as it happens, our input is also now going to be 1. So that input goes into the first gate. Now there will be no change in outputs during that first phase. However, question here now, during that first phase, even though there were no change in outputs, does the second gate get any input? Right, so the first gate got the new input of 1. Right, there we have it. What about, and now it's sitting there waiting until it can produce its output. But what about the second gate? Does it get an input here or not? By input, I mean whatever goes into S. Quickly.
I'm guessing no.
Why not?
Because you said we're waiting for the clock to get to phase 0 for change to happen. Am I understanding that right?
Yeah, that is right. So nothing, this 1 that just entered the first gate, right here we have it 1, will not come out at the end of it until it goes into phase 0. However, this is the second cycle, right? And there was already a first cycle, and there was a phase 1 and phase 0. And in the phase 0 of the first cycle, the initial 0 came out of x1, right? And now it's ready to go into x2, right? So that's why x1 can go into x2, right? So let's see. But there's still zeros, right? So because the first input was 0, the first output was 0. Okay, so now we go into the phase 0 of the second cycle, right? And now the 1, right, so that entered x1 should come out, right? So there it is, right? 1 comes out. Okay. So the first bit, which was 0, passed through on the first cycle, and then the second bit, which is 1, passed through gate 1 on the second cycle. And the 0 that came out from the first cycle now becomes the value of x2. Right? Now, it really didn't change its value, right? Because it already was 0, right? But the green 0 is what it was before, and now it received the 0 from the first gate. So let me pause here. Right. So what we're seeing actually is how this 1 starts to move, shifting from left to right. Okay, let's go to the next cycle. Now, by the way, the third gate, x3, hasn't received any inputs yet, right? It's it's waiting for something to come out of x2 so it can receive it, right? And now, with the third bit going in, the 0, let's see, it enters the first gate. So it sort of appears here at the same time. It enters the first gate and it will exit it, but in the second phase. But then in the first phase, the 1 that just left the first gate goes into the second one. It will come out here. Let's finish the phase. It's confusing. Okay, there is the one that went from the first gate, now it's in the second gate. And the first 0 now enters the third gate, right? So what we're seeing here in the second phase of each cycle is the string, right? Sort of reversed. So we got the 0 that went in first, then the 1 that went after it, then the 0 that went after it, and then the last 0 that went after it. Right.
Professor,
But we're not. Yes.
I'm sorry if I missed this, but what is preventing the flow of electricity just zapping them all at once, or virtually all at
Yeah.
once?
Okay, good question, right? What is preventing is that we just made sure that each gate will take longer than than phase 1, right? But let's say that, fine, phase 1 ended, and now it's ready to shoot through, right? Phase 1 was quick. What prevents them is that during phase 0, clock is 0, right? And while clock is 0, the whole gate is like, it's just like everything, it stops, right? As in T, basically the clock has to be 1 for the gate to produce an output, right? So when clock is 0, it's sort of frozen. So that is what prevents it from shooting through, right? So we only needed to artificially slow it down during phase 1, because during phase 0, nothing happens. It will not. It will not. During phase 0, it cannot accept input, right? During phase 0, the previous gate can produce output, but the next gate will not be able to receive input, right? So if we think about it in time, well, you know what? Let's do it right now. We have one more 0 to go. So that last 0 now will enter the first gate. Its state is still 0. It gets a new 0, right? During the phase 1 of the cycle, right? And then all of the other 2 gates also get their inputs, which were previous outputs from the previous gate, right? But there is no change in outputs. They only get their new inputs, right? So with the last 0 going in the first gate, right, the second gate gets the previous 0 from it. The next gate gets previous 1 from, and then the last gate's 0, right? So these are all the inputs, right? Now, once we get, but just to pause here, during phase 1, only the inputs come in, right? And that is when the clock is on. When clock is off, right, after that fast moment happened, there is plenty of time to the outputs to go out, right? But they will not be accepted into the next gate in the chain until we get to the following phase 1. Does that make sense? So here we have, after the last 0 entered here we have the state of the 3 x's. It's 0, 0, 1, right? So we see that this 1 has shifted through the 3 gates, or the 3 bit registers. And then on the last cycle, here we have them. The input 0, 1, 1, 0, 1, 0, 0, 0. on the last 0, it's going to push the 1 out completely. Right? It will just sequentially 0 out all of the gates, and eventually, when we get to the phase 0 of the last cycle, that last one is going to be replaced by 0. Right? That will be the value of x3. So this is probably the trickiest device that we have seen this semester, and that's why it's the very last thing. But it is within the scope of the semester. You need to understand it for computer architecture too. So what I will do here, because it's so convoluted, is rather than giving you PDF slides of the finished slide, or I will do that, but I will also give you a link to the well, either iCloud, or I can also do PowerPoint, which you can go through it step by step. So when you review it, it may be helpful for you to go through it step by step, right, as I do during the lecture. But look, before we move on to review, ask me some more questions about it. We have plenty of time. Right. Actually, there is one more thing before review. So let me show you the trick how the flip-flop gate is slowed down. No, where is that? Oh, it's in a different slide. No, it should be here. Okay, here it is. So we're going to use the clock itself to slow things down. So what I have here, these 2 green boxes, what are they? They're flip-flop gates, right? And they're identical to each other, right? There are 2 NOR flip-flop gates, but they're clocked, right? So the S and R for each of them are controlled by the clock, right? So for each of them, we have SR clock. Yeah? Now, what about the clock? Where does it come? Well, it comes from the system clock and goes in here. And then it's split, and we're sending the true clock signal to the first flip-flop, and the inverted, the complement, to the second flip-flop, right? So what happens is that during the phase 1 of the clock, when it's surging, the first flip-flop gate is active, and it just shoots through, right? But during this very quick period, that value of 1, right, becomes value of 0 for the clock input of the second flip-flop gate, meaning that it, even though the signal shoots through the first flip-flop, the second one will not accept it until its input clock input changes from 0 to 1. So it waits a little bit, not too long, because that one clock impulse is very quick. So after like an instant, clock becomes 0. So this first gate is done. But the reverse of clock becomes 1, right? And now the second clock wakes up, right? And it can shoot through its result. So what we have here is 2 flip-flop gates, sequential, right? Feed from one to the other. But one is clocked with the system, and the second one is clocked with the reverse of it. Okay. Now, when we put a pink rectangle over the whole thing, we get a single flip-flop gate effectively that will not run faster than the phase 1 of the clock, right? So basically, this is how we solve the racetrack problem. We make a slightly complicated flip-flop gate that is just 2 flip-flop gates together, synchronized. The first one is the input is clock, true value. The second one, the clock input is the complement of the clock. So this is actually quite simple. Does this make sense to everybody? Right, so this is how actual flip-flop gates are made. They're sort of made out of pairs of flip-flop gates. Any questions, comments, thoughts about this? It's good. Okay.
So this is sort of similar to the full adder being made out of 2 half adders. That's
well,
okay. Respond to that.
Well, no. The question, no. It's a good question. The question is it similar to full adder being made of 2 half adders? It is similar in the sense that we are composing larger circuits of smaller circuits. Yeah. The difference, though, is that the adders, or at least the way we looked at them, they don't sort of like exist in time. They don't need to be synchronized to anything. I mean, in real life they are, but the way we looked at them, it's just, we have a bunch of sequential circuits, and they do calculations for us, right? Here, or another way to say it is for, putting together adders and subtractors after half adders, out of half adders and half subtractors, there is no control, right? So these flip-flop gates are now what is called controlled input, right? Where in addition to the set and reset input, they have the clock, right, or control, right? And yes, we're composing one flip-flop gates out of 2, flip-flop gates, but it's all connected to that clock control, right? And we're doing a trick here by splitting it and reversing 1/2 of it to affect how it functions in time, right? If we ignore time, it functions just like a regular flip-flop gate, right? If both are zeros, the outcome is previous state. If S is 1, the outcome is 1. If R is 1, outcome is 0, right? So a flip-flop gate is a flip-flop gate, right, no matter what. But this particular flip-flop gate, and of course, when we have control flip-flop gates, we need the control input, right? So the big one has control, the big one has the clock input, the small ones also have their own little clock inputs, right? But what the big one guarantees is that it will not, the signal will not shoot through it faster than the phase 1 of the system clock. I don't know if that answered your question.
It's fine, thank you.
Okay. I think this one is actually pretty. It's very clever. Whoever came up with it. It's pretty simple, right? So during phase 1 of the clock, the signal goes into the first flip-flop, but gets stuck in between first and second flip-flop, right? Because second flip-flop is not enabled, right? Because its clock input is 0. So it shot through the first one and then got stuck here. Now, during the subsequent phase 0, right, of the clock, the first one gets disabled, but we don't care because the signal already went through it. Now, during the phase 0 of the clock, inverted here, it becomes 1, and the signal can finally go through flip-flop 2. And the output of flip-flop 2 is also the output of the big flip-flop, the whole thing. So the big flip-flop solves the racing problem or the racetrack problem. So I think this one is pretty straightforward. How do you feel about this one?
I guess
Yeah.
there will be no homework due, but are there any homework problems for this that we can sort of just think about?
Well, I think you have to think about this one, right? There is no. So if I will ask you, a question about this on the exam, it's going to be a question about this exact circuit. There will be no changes. Like this is it. This is the one that you have to understand. I think that what will be helpful for you is to go through the 5 cycles, right? Why 5 cycles? Because we have 5 bits that we're throwing at it one after another, right? And we simply want those bits to shift through the register, right? So they all start, the 3 X's start at 0, right? And then on the first cycle, we put in the 0, and it goes into the first flip-flop and sets it or resets it to 0, right? So it doesn't actually change, but the green 0 is what it was before. The red 0 is what it's now. Then it cannot continue, right? Because of how internally each of these gates has, 2 gates with a reversed clock, right? So and then it waits, right? So now the second cycle starts, right? And on the second cycle, the 1 bit is thrown in here, right? It's thrown into the first gate. And during phase 0 of that second cycle, it will actually set that gate to 1. So x1 becomes 1. Now, sorry, here, x1 becomes 1. This is it. Now, at the beginning, on the first phase of the second cycle, the 0 out of the x1 was sent to x2. And on the phase 0 of that cycle, phase x2 will actually change to that 0. So here we have it. On this phase 0 of second cycle, x1 went from 0 to 1, and x2 went from old 0 to new 0. Right? The x3 still hasn't changed at all, right? Because the sort of like proliferation of these input bits hasn't reached it yet. On the third cycle, in the first phase, we have the new input bit. It's 0. And the values, the states, right, of the states or the outcomes of these 3 gates will not change during phase 1, right? So we're in cycle 3, phase 1, right? So if you notice, whenever we go from phase 0 of previous cycle to phase 1 of the next cycle, right, the state of x1, x2, and x3 doesn't change, right? And that is by design, right? The state will only change during phase 0, right? During phase 1, it can receive inputs, but the state doesn't change yet. Only during phase 0, when there is no new input, then the output or the state will change. I interchangeably use the output, which is q or x1, and the state. If you think about it, that is where the flip-flop stabilized until there is new signals going in, right? So after or at the end of the cycle 3, phase 0 of cycle 3, now x1 receives the 0, x2 receives this one, and x3 finally takes on the state of that first 0 on the string. So it went from its original 0 to that 0. Okay. Now we keep sending more zeros, right? We send 0, 4, another input signal, into the system, right? So that's the new input. Now, what are the inputs to x2 and x3? Well, the inputs to x2 and x3 are the what are the outputs of the previous two gates, right? Or so now when we go to phase 0 of the fourth cycle, now x1 takes the value of this 0, x2 takes the value of this 0, x3 finally receives that 1, and that first 0 that was sent in finally falls off of the x3 and overflows somewhere, right? It's gone. Right? And then we have the last bit in the string, 0, right? So we go to cycle 5, phase 1. The input is 0. The internal states of the 3 flip-flops are the same as they were in phase 0 of the previous cycle. Now, in the phase 0, the last cycle, their states change, right? So for x1 and x2, they just get another 0 from the left. And so does x3, and that 0 finally knocks out the 1 that was its previous value. And in these 5 cycles, we saw the 1 travel through these 3 flip-flops from left to right, and sent on its way to the right. Ask me more questions about this, right? So one thing when you're looking at this diagram, right, at the slide, one thing not to confuse is that when we go from phase 1 to phase 0 and then phase 1 and the new cycle, it's easy to start thinking of it as input and, but they're not. They're all output. They're present state of a flip, right? This is the input that goes into the initial one. You can try to conceptualize it in any number of ways, and that's fine, right? Because you can sort of like assign temporary values to these wires, right? But this table, this truth table, whatever it is, right, doesn't represent the inputs and outputs. It represents the current state of each of the 3 flip-flop gates, right? x1, x2, x3. It also represents as input state of the clock. So it's phase either 1 or 0. And this is the input, the total the input into the system, right? It's the string. So each bit in the string. I know this is hard, but this is something that you do need to learn. Why don't you ask me more questions about it? Right, this is how systems are actually built. Like, this is how they actually work. What I will say is, sorry. The first thing that we did, right, today, yeah, here, this one. Right, before, when they just showed you the simple T flip-flop, people were asking, oh, like, what's the point of it? Just, alternates between 1 and 0. Yeah, it does, but the real systems have something more like a JK flip-flop that will do that under certain input. But under other inputs, it will do other things, right? So it can preserve its previous state, or it can be set to the input, which in this case would be J. Only with both J and K are 0, then it goes into the sort of like standby oscillation mode, right? Where it will oscillate between 1 and 0 at half the speed of the system clock. Should I go through this one more time, or is it at this point diminishing returns?
I think
Okay.
you could go over maybe one more time.
One more time, yeah. All right. Okay, we have a little bit of time. You know what? Let me just quickly go through the review slides, and then if we have time, then I'll go to, I don't want to just keep repeating, but I understand the need for it. Okay, so what is going to be on the exam, right? Here, review. Okay, so on the review, we're going to have minimization of functions, right? K-maps, tabulation table, don't care conditions, circuit design, right? So some of you use the textbooks version of how to draw a K-map. On the exam, please try to use this one, right? So where we have four inputs, it's x prime, y prime, z prime on the sides, and t in the middle, t prime top and bottom. So we're going to do adders and subtractors. Controlled circuits is what we've been learning just now. Flip-flops just now. Okay, so what else is going to be in the exam? So here I'm going to pose these slides. Here
I'm sorry, on the previous page
example.
you said there's some mention of homework, but
no.
Worked out the JKFF homework.
I'm not going to have that on the exam. Well, I mean, look. Well, no, I will. This is it. This is the homework. I didn't assign it as a homework, but I just explained it to you, right? So this will be on the, or this can be on the exam, right? This is the JKFF. FF stands for flip-flop, right? So this thing that this slide mentions is on the previous slide, right? It's right there. It's just that, normally I would assign it as a homework, then I would explain it, then it refers to this. Okay? Okay. So this would be, again, I will pose these. This would be an example of a question about controlled circuits. And as I said before, you want to do first the truth table, then the minimal forms of the function, and only if you have time, draw it, right? Now, once you have a minimal form, drawing is sort of like really straightforward, right? So you have not, multiply, or not multiply. So each one of these will become an AND or an inverter, right? So each of these pluses, there are two pluses, will become two OR gates, right? Everything that is inside the product that goes into the OR, right? Three terms become the three inputs, right? So 1, 2, 3, and then each product is AND with three inputs, right? And whenever you have complement, it's an inverter. But as I said, the truth table and especially the minimal forms will be the most of the credit, and then the diagram, if I ask for it, is sort of like the icing on the cake. Right. Then we're going to have adders and subtractors made out of half adders and half subtractors. Notice that this is going backwards in the semester. Notice that there is no control here, there is no clock here, right? They're just sequential, and they can move as fast as they want. Right? Okay. And we're going to have the minimization example again. So if we're going to minimize a simple Boolean function, right? You want to do truth table first, then K-map, then from K-map come up with a minimal form, right? And then once you have the minimal form, if you have time, you draw the diagram, right? So here we have 1 plus, which is this is the OR gate. We have 2 multiplies, which is these 2 AND gates, right? And these AND gates get x, y, and xz literals, x, y, z. So x and y, right, and z are all complemented, right? So we need to have these inverters. Okay. Right. Now that's for A. What about B? B is just straight up Z, right? So in order to have an inverted Z going into the first product of A and a true value of Z going into B, right, we have to split it here. And then, yes.
For that one, if there was like a condition where like for this number it never occurs, would we put D?
Yeah, they do not carry condition. I don't think it would come up here. So we're sort of going backwards. Let me just, so this is the first thing that would be the first, well, one of the first topics that would be on the exam is just the minimization, right? Where how to do the K-map with prime implicants, right? And then how each prime implicant will represent multiple of these, right? So this is, let's say, the beginning of the topics. So once you understand how to do the how to extract prime implicants and minimal forms from a K-map, right? Then we move on to you know, sequential circuits where you have multiple parts, right? Where you have, let's say, you know, multiple functions coming out of the same output, same input, right? So we have, you know, input x, y, and z, but then we have 2 functions, a and b, right? And something like that comes up with adders and subtractors. So then we have truth tables for those. Then we go to control circuits. And then we have, so this is basically the outline, right? What we have: minimization, K-map tabulations, do not care conditions, right? So the last example of do not care conditions that we looked at were those doors that go in and out. And then there were other homeworks on don't care conditions, so review those, right? That's when you have a K-map and you have some ones, but you also have Ds. Right? So if you have the ones, they must be covered by an implicant, but the Ds don't have to be covered. You can just use them to make really big implicants. Right? This homework that this slide refers to is it's this one, and this is the solution to it. Okay, so we have a few more minutes. Should I use them to let's see, go over this chain of 3 flip-flop gates again.
I would prefer if you went over a tabulation example.
Tabulation. Okay, let's do that.
I was gonna say the same thing. Yeah.
Okay, great. So let's do that. Let's find it. Tabulation.
Wait, will we have tabulation? Because on the topics that you mentioned, it didn't include tabulation.
Let's go over it quickly just in case, so that I haven't made the exam yet. Or I haven't made this version of the exam yet.
Or rather, it's something that we could do to minimize the functions, but it's not the only way.
Yeah, right. That's the real thing. But you need to understand how it works, though, right? So who was the last student who spoke? I'm not going to punish you, Jordan. Yeah, no. What Jordan says, right, is that whatever can be achieved by the tabulation method can also be achieved by simple use of prime implicants with K-maps. And the tabulation method is sort of more for the machines than for people, but it's really not that hard. You will need to deal with it in computer architecture too. It's really like step by step. It actually requires less imagination than the K-map method. It's true that it's probably not the best use of this remaining time for me to go over it because it's slow. But let's say that it's unlikely that I will ask you specifically to do something using the tabulation method. I probably will not do that, right? So that's why it's not listed on the review slides. So let's just leave it at that. It's something that you probably should go over before the next semester starts on your own, okay? Other questions or requests? Right, no, I will not ask you to artificially do something using the tabulation method on the exam. What should we look at? No requests at all. Everything is good. So I must right now, right after, well, I have the lecture right after this, so that will last another hour and 15 minutes. So if you do not see these last 2 sets of slides appear on the outline in the next hour and a half, then start sending me email reminders, right? So I need to put these slides on so that you can use them for the review. And I also, I'm going to make sure to, in addition putting these slides on, I'm also going to put a direct link to a step-by-step version of this so that you can follow it step by step.
You don't happen to have a copy of the review slides without the solutions that we could sort of do on our own?
Can you say that again?
You don't happen to have the review slides without the solutions so that we could try to work those out on our own?
Yes. So what you this is yes. So this is how you would do it. I'm going to post direct link to the last lecture and to the review slides, and this is what you would do. This is how it would work. So, for example, right, you would run it like a slideshow. You'll see in a second.
Right. Okay. Thank you.
And then you would see it before the solution is filled in. right? And then I guess it will be, well, so you should be doing it on paper, right, next to the computer, and then if you stumble, you just hit next, and one by one you'll see the. So that's the problem, and then the solution. So I will post both of these as slides and as links. Okay, I'll do that. I promise in the next 2 hours. If you don't see it in the next 2 hours, start sending me reminder emails, everybody. I also ask you to, if you haven't done the teacher evaluations yet, we're not at 50% yet, so please do the teacher evaluations. Other than that, I need a 50% response rate, basically. And other than that, just prepare well over the weekend. The exam is open book, whatever that means, but you obviously have to solve problems in real time. And we're going to start, if you were late, at 11, right? So I'm going to give you like extra 40 minutes for the exam. Some of you who have other classes cannot join us at 11. Join us whenever you can. So everybody will have at least, let's say an hour and 40 minutes. I just want to make sure that I'm testing your knowledge, not how fast you work. So I want everybody to have plenty of time on the final. Okay, so if that is all, I'm going to stop recording. And there were several people who wanted to talk to me in the office hours. Would you mind raising your hands, everyone who, I'll stop recording, who would. I accidentally kicked myself out of the session, but I'm still here. I'm back. Okay, I'm back, and we're all here. So everybody who needs office hours right now, please raise your hands. Okay, Boris. Okay, Boris, can we have office hours in about an hour and 15 minutes? Would you be around then? Hello? And because I have to start my lecture and my other lecture, but I want to talk to you. Would you be around? And so if it's 1:15 now, would you be around 2:30? I can't hear you. Could you type your response? I see your microphone going in on one and off. Boris, can we have office hours at 2:30?
Hello, is my microphone working?
Now it is, yes.
Okay, yeah, yeah, I can do that. It's a very quick question. It shouldn't take that long.
Well, if it's a quick question, okay, then let's do it now. Okay, let's do it now.
Okay, you sent me the email, like my grade scope for quiz 2.3, like way back when. I thought like the picture wouldn't submit, and you said to forward the email. If it didn't, but like the pictures did submit. I was wondering if you wanted me to do the same thing for quiz 2.2, which I submitted through email.
Yes, please do that, and don't make a new email. Forward that original email. Okay.
For the okay, got it.
Okay.